Good morning. Today we're going to learn something new, how to write electron configurations. So elements are composed of protons, neutrons, and electrons. The number of electrons in a neutral atom are equal to the number of protons, right? The number of protons is the atomic number, which is given the symbol Z. So electrons aren't necessarily free to just sort of move around. They actually have homes. And the way that they live in those homes or in those places, we're going to call that their electron configuration. So let's talk about the shape of those homes. The first shape is the s orbital. The s orbital is spherical. It looks like this. It can only house 2 electrons, and the places that these orbitals are located are in the red, orange, green, and purple areas of the periodic table. So that is here on the left. So this is where s orbitals are located. Now, each orbital, like I said, can only hold max 2 electrons. Okay? The p orbital is a little more complicated. It looks kind of like a dumbbell, like a weight that you may lift to work on your biceps. There are 3 possible orientations for the p orbital. You have the px, the py, and the pz. Now, that should make sense if you think that there are 3 orientations in a 3-dimensional space, right? You have your y-axis, x, and z. You'll notice that these orbitals are aligned along each one of those 3 axes. Each p orbital can hold 2 electrons, so the px can hold 2, the py can hold 2, and the pz can hold 2, for a grand total of 6 p electrons. Now, where are these p orbitals located on the periodic table? They are located here. P orbitals. Notice how this is red. This is an s orbital for helium. Now, this extends down. I'm only showing you an abbreviated periodic table just to save space, but this extends all the way down to the bottom of the table. Okay? Now, these orbitals have a specific shape because this is where the electron is in reality most likely to be. So, when you go to college, if you major in chemistry and take physical chemistry, you'll actually learn the equations that describe where you're most likely to find electrons. Those equations describe these shapes. The third type of orbital is even more complicated. It's called a d orbital. These are clover-shaped, and there are 5 possible orientations: dyz, xy, xz, x squared minus y squared, and z squared. You don't need to know those names for the d orbitals. You do need to know the names for the p orbitals, though. Each one of these d orbitals can hold a max of 2 electrons for a grand total of 10 electrons. And where are d orbital houses located? They are located for the transition metals. So here in the gray is where we have our d orbital housing. Right? So any electrons found there are going to live in d orbitals. Okay? Now, now that we know what types of houses look like, we have to give them an address, right? Where are they at? We know what they look like. Where are they at, though? So the periodic table becomes really important because we need to use these numbers on the left. These are called principal quantum energy levels, right? And they're going to help us give these houses an address. So if we start with hydrogen, it only has 1 electron. And the reason why is because it only has 1 proton, right? And it's neutral. And so we can say that that electron, it lives in a red s orbital. And now we can get even more specific and say that it is a 1s orbital. right? The 1 comes from the fact that that hydrogen is on the first quantum principal energy level. So this would be a 1s orbital, meaning it's an s orbital, so it's spherical, and it's located on the first principal energy level. First principal energy level. So principal quantum energy level, first principal energy level, it's sort of the same thing. So we could just call this, you can drop the word quantum basically is what I'm saying. Okay, so now if we look at an electron that lives in a blue p orbital, we can now say that these are 2p orbitals because those orbitals occur on the second principal energy level. So let's go through and look. For the principal energy level 1, there's only one type of orbital, and that's an s orbital. And the maximum number of electrons for there is going to be 2. There are 2 different types of orbitals on the second principal energy level. I'm going to do this in colors. There's the s orbital in orange. This should be red. 2 electrons. There's the s orbital in orange, and then there's the p orbital in blue. The p orbital can hold a total number of 6 electrons, whereas the s can hold a total of 2, right? Here's 2s, here's 2p, right? They're both on the second principal energy level. The third principal energy level additionally only holds 2 electrons. That would be the s again, it holds a maximum of, the green 3s, green 3s, and then we have the 3p, that's a little hard to see, and again that's 6 electrons. Okay, once we get to the fourth principal energy level though, you'll see that now we've added in d electrons there in the center. So we have s for 2 electrons again. Here's our 4s. Then we have the d electrons, which holds a total of 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons total. These are the d. And then we also have the 4p for a total of 6 electrons. Okay? And that's just helping us sort of diagram how many electrons are there. So let's actually try and write out the electron configuration for carbon. If you go and look at carbon, you'll see that it is right here. Carbon has a total of 6 electrons total because it has 6 protons in its neutral. So its electron configuration should have 6 electrons. Now, to do electron configurations, really all you need is to just count starting from hydrogen and working your way towards that atom. So we start at hydrogen, that's 1s. And we go to helium, that's also 1s. So you'll see that we have 2 electrons in the 1s orbitals. Then we keep going, and we get to here, the lithium and the beryllium. That's 2s, right? So we have 2 electrons in the 2s orbitals. Then we get to carbon, right? And we go here, then here. So how many arrows do I have there in the 2p block, right? These are the 2p electrons. And I have 2 electrons, I have 2 arrows there. Okay, so that means that there are 2 electrons in that 2p block. So total, there's 2, 4, 6 electrons. We've got 2 electrons in the 1s, 2 in the 2s, 2 in the 2p. Now let's do that again. How did I do that? So what you do is you go 1, 2. There's your 1s electrons. So you have 2 electrons there. Then I keep going until I get to carbon. 3, 4. Those are in the 2s block. And then I go to carbon. 5, 6. Those are in the 2p block, so I still have 2 electrons. Now, if I'd kept going, if I'd gone to nitrogen, I would have had 3 electrons here. So, how can we make this a little more specific, though? Well, if you'll remember, p orbitals have 3 orientations. So I need to break up the p orbital into its 3 orientations, px, py, pz. You can be even more specific and say each one of those is on the second principal energy level. And so what happens is, right, you keep your 2 electrons in each s orbital, no problem there. But on the p orbital, right, you want to split those electrons up so that they're each staying in their own room. So they're in the 2p house, but now there's 3 different rooms they can live in, the px room, the py, or the pz. We didn't change the number of electrons. It's still 6 total. We're still talking about carbon, but now they're a little more spaced out. There's one final change we need to make. Electrons are represented by chemists as arrows. So you have either a down-facing arrow or an up-facing arrow. And the orientation of the arrow matters. This has to do with a characteristic of electron spinning and its magnetism. Just know that an up arrow is distinct and different from a down arrow. We'll talk more about this later. So, how do I show this now finally? I use arrows to represent each electron. How many electrons are there? Well, there's 1, 2, 3, 4, 5, 6 electrons in carbon. This is still for carbon, right? Remember, carbon has 2 1s electrons. If we go back up to our chart, you got this one and this one. Remember, an s orbital can only hold 2 electrons. Carbon also has 2 2s electrons and 2 2p. So we've got the 2 1s electrons here, the 2 2s electrons here, and then now, since we split the 2p house up into its 3 rooms, each room now has 1 electron. As you keep going, you put the next electron here for nitrogen, and then you could start doubly occupying up each one of those rooms, but not until you have enough electrons. Right? Keep everything singly occupied first, 1 electron in each room until you have enough. So we're going to come back and revisit these rules at a later time. So you can read them now, but we're going to come back and deal with that in the next lecture. So there's an easier way to actually do that electron configuration without having to draw everything. So you can do it in shorthand by just writing it out. So the 1s tells you the orbital type. This superscript 2 tells you the number of electrons. So this is saying I have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 2 electrons in the 2p orbitals. This is still for carbon. Okay, that's carbon's electron configuration. Now, it gets even more complicated a little. There is another type of orbital called an f orbital, and look at how much more complicated it is, or complex it is rather, than even the d orbital. There's 7 f orbital orientations. Still, each orbital can only hold 2 electrons for a grand total of 14 electrons. And then that's just the shape of the f block homes, the f orbital homes. All right. So there is an order that you can list these things in. So it starts with the s orbital. So you could put 2 electrons here, goes to 2s next, then 2p. These are my arrows, by the way. Then 3s, 3p, 4s, 4p, or 4s, 3d, 4p, 5s, 4d, 5p, all the way up, on and on and on and on. Notice the types of orientations, and it even says subshell electron capacity. So s orbitals can only hold 2 electrons max. P orbitals can hold a total of 6, D orbitals a total of 10, and F orbitals a total of 15 electrons. Notice that for p orbitals, you've got your 3 orientations that you do need to know. The D, you have your 5 orientations, and F, you have your 7. So let's actually practice now writing these out. It's actually a lot easier doing electron configurations than maybe it seems like it is. So we're going to do this shorthand style. So let's do it for lithium. Lithium has an atomic number of 3, which means it has 3 electrons. So we always start at hydrogen. Hydrogen is 1s1. That means that there is 1 electron in that 1s orbital. Then we go to helium. Didn't mean to do that. We go to helium, and now it is 1s2. Right? There are 2 electrons there on that 1s orbital, but we're not to lithium yet. So we go to lithium. Now we're on the second principal energy level. That means that we have 2s1. Notice here in lithium we have 2 plus 1 is 3 total electrons. Those electrons are located in the houses of, 1s, which is the red, and then the 2s here, which is the orange. Remember the locations of these orbitals, right? The 1s, here. Right, remember this. This is important. Okay, so the electron configuration for lithium is 1s2, 2s1. Now let's do one that's a little trickier, argon. Argon has an atomic number of 18, which means in neutral form it has 18 electrons. So let's start. We have 1s1, 2s1. 1s1, 1s2. Then we keep going. 2s1, 2s2. Keep going. 2p1, 2p2, 3, 4, 5, 6. Keep going. 3s1, 3s2. And finally, 3p1, 2, 3, 4, 5, 6. 3p6. Right? So a total of 2 plus 2 plus 4 plus 2 plus 6 electrons to give us a total of 18 electrons. Remember, the s orbitals live here. This is also s. P orbitals live here. P orbitals. And then the d orbitals, for now, we'll say d orbitals live in here. This is where the f orbitals live at, lanthanides and actinides. So let's do vanadium. Vanadium, I'm going to erase some of this stuff because it's getting a little crowded. Okay, so vanadium is here. It has 23 electrons. an atomic number of 23 also. Goodness gracious. 23 electrons. Okay, so we always start at hydrogen. So hydrogen is 1s1. We go to helium 1s2. Do lithium beryllium. That's 2s2. We do boron, carbon, nitrogen, oxygen, fluorine, neon. That's 2p6. Keep going. All the way to argon still. But then we have to go past that. Right, now we get to potassium and calcium. Still s orbitals, but now on the 4th energy level. So that's 4s2. Now here's where it gets a little tricky. D orbitals actually don't start on the 4th energy level, even though this row right here is on the 4th energy level. D orbitals start at 3. So this would be 3D, this would be 4D, even though it's on the 5th energy level. So actually when you're writing this, to get to vanadium, you would do 3D1, 3D2, 3D3. So this would look like 3D3. Right, that's a little confusing, or it's really not confusing, it's just something you have to remember, that the D orbitals actually don't start on the energy level that they're at. They start at 3D. So this goes 3D, 4D, 5D, 6D. Right, this is 1s, 2s, 3s, 4s, 5s, 6s, 7s. This is 2p, 3p, etc. Now you'll see that the F orbitals actually look like they start on the 6th energy level, right? The lanthanides looks like it's on the 6th level. But really it starts 4F, 5F. They don't start on the same principal energy level that they're on either. Okay, let us now do phosphorus. Okay, phosphorus is here. It has an atomic number of 15, so 15 electrons. And it actually comes before argon. So we'll start at hydrogen like we always do. That's 1s1, helium's 1s2. Then we go lithium, beryllium. That'll give us the 2s2. We go boron to neon. That's the whole 2p block, so 2p6. We go sodium, magnesium. That's the 3s2. And then we go to phosphorus. So we have 3p1, 3p2, 3p3. Phosphorus only has 3 p electrons on the 3rd principal energy level, 3p3. Remember, these superscripts are the number of electrons. This part out front is what orbital that they're living in. Okay, so let's do another one, copper. Copper is right here. Pause the video and see if you can do copper by yourself. Remember that it's on the 3D block, but 3D is on the 4th principal energy level. Remember that there's that difference. It seems strange, but it's just something we're going to have to remember. Okay, so copper goes Z equals 29 electrons. So we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 4s2 brings us up to potassium and calcium here. Now, copper is on the 3D block right here, and it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3D9. Finally, let's do the last one, which is definitely the hardest one. It's F, and that's because it actually has F electrons. So remember, this is 3D, 4D, 5D, 6D. So lead is down here. Z equals 82. It has 82 electrons. So this is going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So 5p6 brings us all the way up to xenon. So we've listed everything up above here. Remember, this is 4s, then it goes 3d, then it goes back to 4p, right? All the p's are actually on the orbital or the energy level that they say they're on. So now we keep going. We're going to do cesium and barium. That's going to be 6s2. Then, even though this table shows, that you hit a d electron first, list the f orbitals first. So we have 4f14. It's 4 because the f orbitals start at 4, even though they're on the 6th energy level. So we go all the way through those. Then we have to do the d electrons. 1, 2, I'm going to do these in a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they are on the 5th energy level, so 5d10. And now finally we can get closer to lead. We're on the 6th level, so 6p1, 6p2, 6p2. And that is the configuration for lead.